In circle theorem, we will look at parts of circle. The first one is segments. We have the minor segments, the major segment, and we have the chord, which divides the segment into two unequal parts. So you can see the chord there. The chord is there. Yeah. So we have the radius, we have diameter, we have the tangents. Look at the way it is. We have the chord, sector. Also, we have the minor sector. We also have the major sector. We have the arc, minor arc. We also have the major arc. Okay, we have the circumference of a circle. So the minor arc and the major arc, addition of them comprises of the circumference of a circle. Okay, now let's go to the circle theorem, theorem 1. Angle which an arc subtends at the center is twice the angle it subtends at the circumference. We are given the circle center O. Okay. Now we have an arc AB. Let's say we have an arc AB which subtends an angle of theta at the center. The same arc AB subtends the angle of alpha at the circumference. So what we are saying in this theorem is that the angle at the center there, if we use compass to measure it, will be twice the angle at the circumference. So if that is 120, that will be 60. Okay. Now let us consider another one. That's theta is equals to 2 alpha. Let's consider another one. We have the major arc now. The major arc AB. The first one we consider is the minor arc AB. So the major arc AB, it will subtend the major angle at the center. You can see. So let's say angle beta now. So and it will now go and subtend angle gamma at the circumference. And you can see that the circumference there will now be on minor arc. Can you see it now? The major arc now, look at the angle at the center and that angle at the circumference. So we'll say beta is also equals to the 2 gamma. So if beta, for example, is equals to 200, gamma will be equals to 100. In the two scenarios, angle at the center is 2 times the angle at the circumference, and the minor arc and the major arc, the angle they subtend, we can see there. Let's take, for example, we combine the two things together in that way. The two examples given below have been combined together in these circumstances. So as I've said, the theta is equals to 2 alpha, the beta is equals to 2 gamma. Okay, that is for that. Now, we also realize that theta plus beta is equals to 360. That is angle at a point. We can see the two at a point there. Let's look at this example. In the diagram, find x, y, and m. We can get our x to be equals to the half of the 210 there at the center. So our x is equals to half of 210. So we have the x to be equals to 105. So angle at the center is twice the one at the circumference. Angle which an arc AD now subtends at the center. The arc AD subtends at the center and is the major arc, angle, major arc BD rather. Angle which the major arc BD subtends at the center is twice the angle that it subtends at the circumference. That's our x. Okay. Now, we have gotten the x. Let's get the m. We'll now see that 210 and the m, they are angle at a point there. If you add the two together, they are equals to 360 degrees. So our m now is equals to 150 degrees. And we now know that the m will work with y there. Okay, so the reason there, sum of angles at a point are equals to 360 degrees. Okay, so to get y now, y is equals to the half of 150. That is half of m. So you should know that m and y, they will work together because m is equals to 2y. We divide it by 2, divided by 2. So we now get our y is equals to m over 2. So y is equals to 75 degrees. Okay. Now let's move to another question. In the diagram given, find x. We want to find x here, but we have to get the BAD first. You can see the BAD is equals to half of 120 because angle at the center is 2 times the angle at the circumference. So BAD is equals to 60 degrees. And we can also get a reflex BOD. We can get reflex BOD. Okay. That reflex BOD, we can say there plus 120. It will give us 360 degree. So reflex BOD now is 360 degree minus 120 degree. That's sum of angle at a point. So the answer we give 240 degree. Okay. Now we'll consider BADO is a quadrilateral. And that is reflex BOD we have just gotten, which is 240. We have already gotten BAD, which is 60. We are giving 35 there already. We want to get x. So sum of all these angles together, it's equals to 360 degree. That is sum of the angles in a quadrilateral. Okay, we add all of them together. We equate it to 360 degree. Okay, sum of angles in a quadrilateral. So the x plus 335 is equals to 360 degree. So we have the x to be equals to 25 degree. Another question. In the diagram below, find x. To get our x, we can get BOD. BOD is equals to 2 times 50 degree. Angle which an arc BD subsets at the center, that's BOD, is equal to the angle the arc BD subtends at the circumference, which is 50 in this instance. Okay. Now, we can get our BOD to be equals to 100 degree. Okay. So we bring the BOD then. If you look at the BOD there, it's an isosceles triangle. Okay. Where we have the BO to be equal their radius. BO is radius. And the OD is also radius. So BO and OD are radii. And that means that that is an isosceles triangle. So it means the x BODB is also x base angle of an isosceles triangle. Okay, so that's base angle of an isosceles triangle are equal. Okay, now having done that, so we add everything together with 100. So x plus x plus 100 is equals to 180 degree. 2x is equals to 180 minus 100, which is 80. So we have the x to be equals to 40 degree. Okay, let's look at another example. Corollary in this instance, angle in a semicircle is right angle. We can say that AB is a diameter, and once we have the AB to be diameter there, yes, so the angle at the center there will be equals to 180 degree angle on a straight line. So the angle which AB subtend at the circumference is 90 degree. That is angle in a semicircle. It's just a corollary of the first theorem we looked at. So whenever you see a diameter at the tip of diameter, any angle they make, they are equals to 90 degree. Look at another one there. It's also equals to 90 degree. All the angle that's they make, yes, that angle is equals to 90 degree. Look at it. If the diameter make another angle, that place also will be 90 degree, and so on and so forth. Okay, now let's look at another theorem. Angle in the same segment. Okay, let's see. AB divides the circle into two unequal segments. You can see now. So we have the AB there. So it divides it into two unequal segments. So we have, let's say the first one is x. You can see now they both started from AB. From ABX, you can see the x, you can see the y there. They emanate from the tip of AB, both of them, and they are in the major segments. You can see it now. So we can see that angle in the same segment. So x and y, they are in the same segment. We want to prove it out now. Suppose we have AOB angle at the center now, will be 2 times 2x. We also have AOB is equals to 2y. So if we that's angle at the center is twice the angle at the circumference. Okay, so we can now say that x is equals to y, and that is angle in the same segment are equal. So they are both in the major segment. So they can also be in the minor segment. We can see it there. We have the minor segment. You can see it there. Okay, they are in the minor segment. Let's call that one M. And the M will also equals to N. They are also angle in the same segment. Okay, let's look at another theorem. The opposite angle of a cyclic quadrilateral supplementary. Cyclic quadrilateral, when you talk about cyclic quadrilateral, is a quadrilateral inside a circle. All the tips, all the vertices of the quadrilateral will touch the circle. You can see them now. All the vertices, they touch the circle. Okay, when we have another scenario, look at this. It's also a quadrilateral inside a circle, but not all the vertices touch the circle. That vertex there did not touch the circumference of the circle. All others, they touch it. So we cannot say this is a cyclic quadrilateral. It just is quadrilateral inside the circle. So you can see now that all those points now, those three touches the circle, while the point O rather, did not touch the circumference of a circle. So that's not a cyclic quadrilateral. A cyclic quadrilateral, all the vertices, they will touch the circle, the circumference of a circle rather. So x and y there. Look at this ABCD. Suppose we have a circle ABCD where all the vertices touches the circumference of the circle. So x and y there, they is BCD, that is y, and then BAD, we have x. So we'll see that's the x plus y. When we add them together, give you 180. Because when we say they are supplementary, when we say they are supplementary, it means that it's equals to 180 degree. Okay, so that's what supplementary means. Okay, please we should know that. Suppose AD is extended. So we now have the exterior angle of the cyclic quadrilateral. Suppose the exterior angle is M in this instance. There's another corollary that we have to note, that the exterior angle will now be equals to the opposite interior angle. M will equals to N. We also have to note it. Please note that and jot it down. So the exterior angle of a cyclic quadrilateral is equal to the what? Opposite interior angle. And we can also prove this as well. It's equals to the opposite interior angle. Yes, especially if you are the student of IGCSE, we can prove that. To prove this, and it's usually come out there, that a question that's related to this one. We can say K now is equals to 180 minus M. That's angle on the same, on a straight line, the adjacent angle, they're on a straight line. We can also say K plus N is equals to 180 degree. That is the opposite angle of a cyclic quadrilateral, the theorem itself. So K now is also equals to 180 minus N when we take the N to the other side. Now we can say that the first one is equation star, second one equation star star. So we can see that the 2Ks now, they are equal. So equation star is equals to equation star star. So we can now say 180 minus M is equals to 180 minus N. So M is equals to N in this instance now, which has been proved. Please note that the opposite angle of a cyclic quadrilateral are supplementary. So now let's look at a question here. We're given the diagram below. We want to find ADC and CDC. ADC and CDE rather. So ADC now. ADC plus 100, because both of them are opposite. Can you see? So it's equals to 180 degree, and it's a cyclic quadrilateral. That's the reason we are doing it in that way. So ADC will be equals to 80 degree. Okay. That has been done. CDE. We can just say CDE is equals to 100 because it's an exterior angle which equal to the opposite interior angle. Its opposite interior angle there is 100. So the first reason is opposite angle of a cyclic quadrilateral supplementary. Okay. And the second reason is that the exterior angle of a cyclic quadrilateral is equal to the what? Opposite interior angle. Okay. That's clear. Okay. So we have the ADC to be 80 degree there. I think we can say it there. And CD now to be 100 degree. Thanks so much.